A normal healthy human heart has a resting heart rate of somewhere between 60 to 100 beats per minute. So let's say that your heart is beating at a rate of 80 beats per minute. That's 4,800 beats per hour, 115,200 beats per day, and 42,048,000 beats a year. So how does your heart continuously beat and maintain its rhythm? The cardiac conduction system is the answer.
What is the cardiac conduction system? In the heart, there are specialized cells that generate and conduct signals in order to contract the cardiac muscle and pump blood through the body. During normal heart function, the signal is generated in the sinoatrial, or SA node, and propagates through the atria from cell to cell. This causes the atria to contract.
The signal reaches the atrioventricular, or AV node, and passes through the AV bundle. It's then carried simultaneously down the left and right bundle branches to the apex of the heart, and propagated through the Purkinje system to the rest of the ventricles. This causes the ventricular contraction, and blood is ejected from the heart.
The signal that propagates through the heart is called an action potential. We've put together a schematic to show you the different action potentials produced by different areas of the heart. You can clearly see that while some of them look very similar, distinct areas of the heart depolarize in very different manners. The differences arise from different ion channels expressed by different regions of the heart.
This is the action potential for the SA node depolarization, the atrial muscle, the AV node, the AV bundle, the bundle branches, the Purkinje fibers, and the ventricular muscle. So what is an action potential? Excitable cells in your body, such as those in your heart, have a distribution of ions and charge between the cytosol and the extracellular matrix. In a resting cell, more positive charge is concentrated outside of the cell. This gives the inside a relative negative charge. When the cell becomes excited, these ions move across the membrane, resulting in a brief change in membrane potential. This causes the cell to depolarize and an action potential to fire.
In this video, we will be focusing on the action potentials of the SA node and the ventricular myocyte, and describing the differences between the two. The SA node is the pacemaker of the heart, meaning that, under normal circumstances, it will determine the rate of depolarization, which dictates heart rate.
This pacemaker potential of the SA node is due to the HCN channels, which we've shown in red. These channels generate what is called the funny current. Sodium, which is normally concentrated in the extracellular space, will start to move into the cell through these HCN channels.
The slow influx of sodium ions causes a rise of membrane potential from -60 to -40 millivolts. Once the membrane potential reaches -50 millivolts, T-type calcium channels will open. These are shown in pink. Calcium flows down its concentration gradient into the cell, leading to a further increase in membrane potential.
When the membrane potential reaches -40 millivolts, which is the threshold value of this action potential, L-type calcium channels, shown in yellow, will open as well. This leads to further calcium influx and depolarization up to around 0 millivolts. The L in L-type calcium channels means long-lasting, whereas T-type are transient. This refers to the length of activation of each channel type, meaning the L-type channels will be open longer.
During this depolarization, potassium channels open, causing potassium ions to move out of the cell. Early on in this action potential, more calcium is moving into the cell than potassium moving out. This results in a more positive charge inside the cell in a depolarization phase. Later on, the calcium current starts to decrease while a high level of potassium is still leaving the cell. This leads to a repolarization phase and brings the membrane potential back down to -60 millivolts.
Remember when we said a normal heart rate is anywhere between 60 and 100 beats per minute? How fast the SA node depolarizes depends on how quickly it reaches the threshold value of -40 millivolts. If threshold is reached more quickly, the heart will depolarize at a higher rate and beat faster. This occurs during activation of your sympathetic nervous system, also known as your fight or flight reflex. On the other hand, activation of the parasympathetic nervous system will cause slower depolarization and a slower heart rate. Based on the graph shown here, you can see that you will get a variable depolarization rate with autonomic nervous system activation.
While we focused on the action potential of the SA node, it isn't the only area of the cardiac conduction system with pacemaker potential. The AV node has similar properties and a similar action potential to that of the SA node.
However, the AV node has a slower depolarization rate at only 40 to 60 beats per minute, due to an increased time to reach the threshold voltage. As a result, the SA node overrides it. This means the AV node will only act as a pacemaker in the case that the SA node malfunctions or doesn't fire. Now let's look at the action potential in a ventricular myocyte. The ion channels found in these cells are different from those in SA nodal cells. Ventricular myocytes do not have HCN channels or a funny current, and as a result they have no pacemaker potential. This means that ventricular myocytes can't generate their own action potential and have to be depolarized by a neighboring cell through gap junctions.
Instead of a pacemaker potential, ventricular myocytes have a resting membrane potential of negative 90 millivolts. This is shown as phase 4.
This low membrane potential is maintained by the IK1 channel. This channel allows potassium to exit the cell if some sodium or calcium happens to leak in, preventing depolarization.
If the depolarization coming from a neighboring cell reaches a threshold of negative 70 millivolts, an action potential will fire in the myocyte. The first channel to open are the sodium channels, which aren't present in the SA node cells. When these channels open, there is a fast influx of sodium causing an increase in membrane potential. This is the start of depolarization, indicated by phase 0.
At around negative 20 to negative 30 millivolts, the L-type calcium channels open, causing an influx of calcium and positive charge. The sodium channels are quickly inactivated, but these calcium channels remain open. Eventually, potassium channels will open to counteract this depolarization, leading to potassium efflux. This causes a plateau phase, which is depicted as phase 2 on the graph. During this phase, the charge coming into the cell, the calcium ions, is relatively equal to the charge moving out of the cell, potassium ions.
During phase 3, the L-type calcium channels close and the only movement of ions is potassium moving out of the cell. This results in repolarization back to the resting membrane potential of negative 90 millivolts. Other areas in the heart require depolarization from neighboring cells and have action potentials similar to that of a ventricular myocyte. These include the atrial muscle, AV bundle, left and right bundle branches, and the Purkinje fibers. In a normal functioning heart, these areas have no pacemaker potential. However, if the heart becomes damaged, they could spontaneously depolarize, resulting in arrhythmias.
To end this video, we've created a summary of the differences between SA node cells and ventricular myocytes. Feel free to pause the video here and make sure you understand everything we mentioned. Thanks for watching! Good luck with your studies!